Hi, my name is Simon Ilyushenko, and I'm a software engineer on the Google Earth Engine team. My title here says teledetective because télédétection means remote sensing in French. And today I will talk about the remote sensing and other data in the Google Earth Engine data catalog. Since the beginning of the Earth Engine project in 2010, we have been adding datasets to Earth Engine. And by now, we have accumulated a lot of different data. We have about 35 petabytes of public data in over 700 datasets. We are adding about 1 petabyte per month. I will talk about a few specific datasets, but first I want to give you an overview of the whole catalog. One of the most important features that we have is freshness. All the datasets which are being produced are being downloaded and ingested every day. And sometimes it's even more frequent than daily. For some of the most important datasets like GOES, Landsat, and Sentinel-2, we run jobs to ingest data in near real time. So as soon as we see a new scene, we download it. And so within about 12 hours after its production, it winds up in Earth Engine. Another important feature of the data catalog is uniformity of data formats. Regardless of what format the data originally were in, we put all of them into similar looking image collection or feature collections. And so if you learn how to access one of them in code editor, you immediately know how to work with the rest of the data. However, while we make the data formats uniform, the data actual values are preserved as closely as possible to the original values. So you can go and compare the files you download from data provider with the files you see in Earth Engine. We also provide extensive documentation. We describe everything that's in the dataset, what the bands are, what the units are, maybe there are bit masks. We also provide links back to the data provider if you want to see additional documentation. And we provide the license information so you can see what the terms of use are. And now I'd like to talk about a few important datasets. Sentinel-1 GRD is one of our highlights. It's a radar dataset, so it's important difference from the optical datasets is that radars can see through the clouds. And that means that with Sentinel-2, it's easy to go and see what happened on the ground, for example, after a hurricane, when there are still clouds hanging in the air. With Sentinel-1 data, you can see extra flooding which has occurred. Sentinel-1 can also show you different crop types. Sentinel-2 is another very important dataset. By now, we have almost 15 million scenes. We store both the original TOA data and the surface reflections or SR data. We download both of them from ESA's Sci-Hub site. Sentinel-2 is also mirrored to the Cloud Public Datasets bucket, which means you can go and look at the original files that we put there. And to continue with the Copernicus Sentinel constellation, we have Sentinel-5P. It carries the Trapomi instrument, which measures the concentration of various gases in the atmosphere. And so you can see a daily record of gases like CO, methane, ozone, and so on, and as well as the location of clouds and presence of aerosols. Using Sentinel-5P, we were able to look at the differences between 2019 and 2020 in the early months of the COVID pandemic. And we looked at the presence of NO2 in the air. NO2 is associated with industrial activity and transport. And we published a Medium blog post which shows what changed over 1 year. Now, we shouldn't attribute all the differences necessarily to COVID because there are also natural differences from year to year. But nevertheless, this post shows you one way of analyzing the data and trying to derive some insights from it. To continue with our important datasets, the next one in the so-called Big Three is Landsat. Lancet is a series of US satellites which have been flying since 1974, so they provide the longest continuous record of remote sensing data. We have all of the Lancet data going back to Lancet 1, and we also compute surface reflectance using a Docker image that USGS has provided for us. Lancet data are also mirrored to cloud public datasets. Finally, in the big three, we have MORIS. MORIS is a pair of US satellites that have been flying around the Earth since 1999. They provide daily low-resolution coverage. And not only we have the observation data, we also ingest a number of datasets with derived products. For example, showing presence of fire, snow pixels, the albedo characteristic of the surface, and so on. There are many more other datasets in Earth Engine that I don't have time to talk about. I just want to highlight the presence of a number of climate and weather datasets. Now let's go and talk about a couple of datasets we have added this year, which are particularly important. First, let's talk about GOES. GOES 16 and 17 are geostationary satellites, which hang in approximately the same place above the Western Hemisphere. And they send an image of the whole disk that they see every several minutes. The image is recorded in 16 spectral channels. On this slide, you can see the matrix of all the GOES datasets we have. On the right, we see the optical data. They either provide the view of the whole hemisphere or just of the continental US. And on the left, we see specifically the fire data. This is a dataset derived from the observations showing the presence of the high temperature hot pixels, which probably indicate fire. On this slide, we see one of the GOES scenes shown in code editor. And on this slide, we see the fire pixels, which are exaggerated deliberately so that they're visible at a low zoom. Finally, since we have both GOES fire and optical data, we can combine them in animations like this, produced by Justin Broughton. In August 2020, when we unfortunately had fires going all around the Bay Area, we created this image to show how the fires produce smoke plumes. Now let's talk about Sentinel-2 cloud probability dataset. And by the way, I want to thank Kurt Schwer for uploading both GOES and Sentinel-2 cloud probability data. Removing clouds is an important and not fully solved problem for optical imagery. Clouds are hard to detect. It's not enough to just look for white pixels, because white pixels can be present due to snow or due to white roofs. And so people have been trying to produce more and more accurate cloud masks. The algorithm that we have been running is called Sentinel-2 Cloud Detector. It's an open source toolbox provided by ESA. It's using an ML library called LightGBM, which is a gradient boosting framework. In 2020, we ran this algorithm on all of the Sentinel-2 scenes we have. And now, as soon as a new Sentinel-2 scene comes in, we immediately process it with the same algorithm and put the results into a separate image collection. So now you can join those two image collections and remove all the cloudy pixels from Sentinel-2 scenes. This is one of the examples of the derived data. This is a mosaic of Sentinel-2 imagery of the continental US in 1 month of 2019. And we can see that in the western half, where there are a few clouds, we have all the pixels. And in the eastern half, sometimes all the images were too cloudy, and so sometimes we are dropping data. This slide shows you the presence of clouds in the optical imagery on top, and the cloud probability for the same image for the same area in the bottom. And you can see with visual inspection that here the algorithm did a pretty good job. Finally, we use the cloudless dataset as an input to the next derived dataset, which is called Dynamic World. It's a joint project between National Geographic, WRI, and Google. But there is a whole separate talk about this by Chris Brown, which I invite you to watch. This is all I have for you for today. Thank you for watching, and let us know if you have any questions or comments.